Okay, so I think it's time. So let us start. So in the last lecture, we started discussing about optimization in deep learning, right? And obviously we did not complete it. But what we discussed last time is gradient descent, the challenges with gradient descent, batch gradient descent, challenges with batch gradient descent, stochastic gradient descent, challenges with stochastic gradient descent, and finally we talked about mini batch gradient descent. So broadly speaking, these are the four things, four algorithms that we talked about. What we could not cover were some of the terminologies that are introduced while talking about these algorithms, be it epoch, be it batch size, be it iteration, and there are some terminologies that we did not cover in the last lecture. So let us start from there. Let us revisit the mini batch gradient descent algorithm, because that has all the components, and then let us try to make sense out of each of the terminologies that appear in mini batch gradient descent. And let us start from there, and from there we'll go somewhere else. Okay, so that is how we will start today. So okay, with that, let us start. Right, so this is what, lecture 7. So in the last lecture we talked about, we discussed gradient descent, batch gradient descent, stochastic gradient descent, and mini batch gradient descent, right? So we talked about these four things. So let us revisit the algorithm for mini batch gradient descent, and you should be able to tell me that, help me with that. So algorithm for mini batch gradient descent. So before we start with the algorithm or start with revisiting the algorithm for mini batch gradient descent, can you quickly remind me what is mini batch gradient descent? What we do here? How is it different from, let's say, a batch gradient descent or a stochastic gradient descent? So, what we do? What we do in mini batch gradient descent? We update after each mini batch. Gradient descent we update after we pass over all the data points. Stochastic gradient descent we update with each data point. Mini batch gives us the balance. We update after every few samples. Not every sample, not all samples, every few samples, right? That is what mini batch gradient descent is. So that should get reflected in the algorithm as well. So for let's say I in range epochs, right? You initialize the gradient calculation d theta is equal to 0. You initialize the counter, so count is equal to 0, and then the gradient calculation loop starts. So for x in zip capital X, for x in zip capital X, what you do is you calculate the gradient and update it. So d theta is equal to d theta plus grad theta, that is a function that will probably give us the gradient, and it is function of x and what, theta. Okay, so calculate this, and one more thing you do, because you have to track whether the mini batch, because you have to track the mini batch size, so you also update your counter. So count is equal to count plus 1, and now you can check that. So, if count batch size is equal to 0, then you go ahead and update. So, theta is equal to theta minus eta d theta by b, and also because you have updated it, you set your gradient to be equal to 0, and if and for maybe one more and for something like this, right. So, this is your mini batch gradient descent algorithm that we discussed last time around, right. Now, here what are the terms that we have not discussed? One is epoch. What does epoch means? Those who have done a course on optimization, you probably know about iteration, but is epoch iteration? Is epoch not iteration? If not, how is epoch related to iteration? Is there a relation? Are they two distinct things? We have not discussed. Second thing is mini batch or batch. In this case, batch size. So, what is the batch size? And does it have any relation with epoch or iteration? How the batch size varies between the different algorithms we discussed last time, and so on and so forth, right. Thirdly, because we are solving an optimization problem, there has to be some iteration. So, naturally, what is iteration? If epoch is not iteration, let us say, then what is iteration? If epoch is iteration, then we are good. We know epoch is iteration, it is just another fancy name. So, these are things that we have not discussed, we could not discuss last time. So, let us try to go through each of these terminologies and make sense out of this terminologies, right. Okay. So, with that background, let us start. Okay. So, terminologies used in deep learning. Okay. And when I am saying terminology is used in deep learning, I mean terminology is used while in training of deep learning, in optimization for deep learning, and that is what I mean. I am writing deep learning, but that's what I mean is terminologies that we use for optimization in deep learning, right. So, first thing is epoch. So, the first thing is epoch, or I should say number of epochs, because that should automatically tell us what is a epoch. So, number of epochs is the number of times your algorithm is going over the complete data set. So, what is a epoch? One pass over the complete data set. Number of epoch is number of times your algorithm is going over the complete data set. Okay, clear? So, number of epoch is number of times the algorithm goes over the complete data set. Okay. So, now if you see any deep learning paper, you will see that the models are getting trained for 500 epochs, 400 epochs, 200 epochs, 1000 epochs. So, what does it mean? 500 epoch means the algorithm went over the data set, the complete data set 500 times. Clear? What is epoch, right? Great. So, that is the epoch or number of epoch. The epoch is epoch is one pass over the complete data set. The second thing is batch size, right? batch size. Okay. The second thing is batch size. Batch size is the number of samples after which your model gets updated. The number of samples after which your theta is updated. Okay. So batch size is number of samples after which theta is updated. Okay. The third thing I talked about was iteration. Okay. Number of iteration is equal to number of times theta is getting updated. So one iteration means the theta was updated a single time. Two iteration means theta got updated two number of times. Okay. So the third one is iteration. Iteration is, one iteration is equal to one update of theta. Okay. So three terminologies from last lecture that were pending: number of epoch, number of times the algorithm goes over the complete data set. So a epoch is one pass over the complete data set. Batch size, number of samples after which theta is updated. Iteration, number of iteration is equal to number of update. So one iteration is equal to one single update. So these are the terminologies. Okay. So epoch is basically not iteration in a generic sense. In specific case it can be, but in generic sense in deep learning, epoch and iterations have two different meaning. Okay. So now with these things, let us see in the three algorithms that we discussed: batch gradient descent, stochastic gradient descent, and mini batch gradient descent, what this turns out to be. What is the iteration, what is epoch, what is batch size, and so on and so forth, right? So let us do it like this. So let me write down the algorithm here. Batch size, and then iteration per epoch. Okay. Which means if iteration per epoch is equal to 1, that means iteration is epoch. For any other number, iteration is not equal to epoch, right? Fine. Okay. So the first algorithm we discussed was batch gradient descent. Batch gradient descent, then we discussed stochastic gradient descent, and then we discussed mini batch gradient descent. So for batch gradient descent, we discussed the algorithm last time. Can you tell me for batch gradient descent, what is the batch size? Total number of samples, because it only gets updated once you have passed over, once you have gone over through all the data points. So batch size is equal to n, then, where n is my number of samples, and what is, how many iterations per epoch? 1, because once you go over all the data sets, then you update. So that means that is iteration, that is epoch, they becomes the same. And this explains why in optimization literature, optimization course, you will not hear the term epoch, because their iteration is epoch, because you will not do this kind of approximations. If you go to stochastic gradient descent in that course, if it is covered, which is generally covered in deep learning actually, but if it is covered, then only the term epoch starts surfacing. For most algorithm, iteration is epoch, but not for this course, not for deep algorithms used in deep learning. SGD, what is batch size? 1, great. And what is the iteration per epoch? N, right? So now epoch and iteration are not the same for stochastic gradient descent. One epoch is equal to n iterations. Mini batch gradient descent, batch size some number, let us call it b, that is what we are using, b, and iteration per epoch n by b. Clear? The terminologies are clear. Now generally we will see that in papers that you will read, for example, for your term project, they will just report batch size and they will report total number of epoch, because that suffices. They will not report what is the number of iteration, not needed. I mean, that is a redundant information once you know these two things. You can always calculate that, and that is fine. Okay? Clear? Great. So now, moving ahead, we are talking about optimization, right? And remember, I touched upon briefly that your optimization or minimization, in specific, here it is minimization, the problem can either be convex or non-convex, right? And for example, in linear regression with least square loss function, the objective function with respect to the weights is convex. In linear regression, what you get is a convex landscape of the loss. Okay. In deep learning, however, it is a non-convex optimization problem, which means you do not have a unique minima. There will be multiple minima, there will be one global minima and then lots of local minima. Okay. So the message is that in deep learning we have to deal with non-convex optimization problem. Okay. So in deep learning we deal with non-convex optimization problem. By the way, given a function, how do you test whether it is a convex function or not? Correct. Take 2 points on that line, on that function, connect them, and that line will always stay above the actual curve. Graphically, if you have a landscape, you take any 2 points on that surface, connect them through a line, and that line should always stay above the curve. If that happens, that is a property of convex function, right? So convex function take 2 points on the function, connect them through a straight line the line stays above the function always. Okay. And if it happens, it is a convex function. So if I have to draw it very quickly, so this is a convex function, right? You know, this, there is only a single minima. Take any 2 points, right? Any points you want, connect them. Any points you want, connect them. The line will always be above the curve. Okay. Above the function, right? The curve. The function is the parabolic function, right? Huh? No. Function is what is on the black line. This is not a value that is function.
No. In the black line also that from above that point, that line also will also consider as a function.
No, those 2 points, the curve, that portion connecting those 2 points. You have taken 2 points, right? So there is a curve that is connecting those two points. That is your curve portion. I mean, what is the point of taking that is not in those points? Okay. So it always stays below. Okay. So this is what convex function is. Non-convex, this will not hold. Take a sinusoid, for example. I don't know. I mean, now you will see that it is not working, right? So it's a non-convex function. And you can see in this function, I don't even know how many optima are there. I draw randomly, and I'm using the term optima because there are multiple minima, multiple maxima. So there are multiple optimas that you get in a non-convex function, right? Now I give a statement that I already gave a statement that in deep learning we deal with non-convex optimization problem without doing any maths. Just by looking and your understanding of the neural network, can you justify why it is the case? That why is there not a single optima with respect to weights, obviously. No maths, I mean, obviously mathematically you can prove it, but let's say no maths, just by intuition of neural network and looking at it. I will ask why. Why does nonlinearity means there will be multiple optima? Can it, I mean, was this function not nonlinear that I draw just now? It was a nonlinear function. It was having, it's a convex. So then why nonlinearity means multiple optima? That can be imaginary also, and you can have one optima.
Gradient can achieve like multiple zero values for.
Yes, but how do you know that?
Because it has one order less.
Yes, but maybe those values are, some of those are imaginary. Does it always mean that a higher order means you will get always, n order polynomial will always give you n real roots? No. There are so many examples, right? There can, yeah, go ahead. Multiple sense of theta will lead to the same output, right? Why? You are right. Permutation invariance. So permutation invariance is the term, you are right. So what happens is that if you change the weights in a certain manner, you will get the same output. And let me show it how. I mean, it's very simple actually. So so in neural network, right? Permutation invariance leads to multiple minima. Okay. So let us take a very simple neural network and see what is happening. So let's say my network is very simple. I have only one single input. Let's call it x. At least one hidden layer I need. So h1 and h2. Okay. And then y. And let's assume for the sake of discussion that B bias is not there. Bias being there will not matter, but I don't want to write it again. So let's assume bias is not there. Now let's say this is W1, this is W2, this is W3, this is W4. Okay. So what is y equal to in terms of x? You can easily find it out, right? I mean, obviously W3H1 plus W4H2, where H1 and H2 are basically W1X1 plus W1X1 and W2X2, and obviously there is a activation also there, right? Now think about it. If I take the same network, right? H1, H2, Y. And let's now say my weights are W2, W1, W4, W3. Not the same sets of weights. I mean, the weights value are same, but they are now associated with different hidden nodes. Will the output change? No, right? So clearly these two, when you permute them, both of them are valid weights. And if one is optima, the other will also be optima. Which means there cannot be a unique optima. There at least have to be multiple optima. And there can be multiple, global optima, multiple local optima, there are multiple optima. Any optima that you can get, you can permute it and get another set of weights that will give you the same value. So these two are basically equivalent. So this, without solving anything, just by looking at this permutation invariance property of neural network, you can infer that it's not not a convex. I mean, it cannot be give you a convex function in that sense, right? Because W1, W2, if you permute, you will get the same thing. Okay.
In this case, we are changing the parameters, but my optima is fixed, so we're not getting multiple optimas.
You will get.
But in this example, we says that optima is still remain the same, but weights are getting same.
Correct.
So the optima is same.
Optima is same. So that's
what. If optima is same, that might be the local optima is the global optima. But
no.
You cannot say that there is.
No. What is the convex function?
Convex function has one global optima.
Correct.
That is the local optima and that is the global.
One optima. In this case, how many optima you have?
It is saying one optima.
No, two. The value being same does not mean one optima. The parameter value, when I draw this point, this was your parameter value. This was your parameter value. This was not the function. I mean, if I have two basins exactly same optima, right? Y axis, x is different, right?
So if you are saying you will have two different optima here in case, how this is a permutation invariance? Permutation invariance means that optima won't change and weights are
no,
changing.
that's not. Permutation invariance means even if you permute the weights, the output does not change. The weights are changing, right? But the output Y is not changing. So
in output also we won't get all the time exact same target, but it will be near to that, but that near won't be same on that.
No, again, I'm saying permutation invariance. I'm not saying the optimal value is permutation invariance. I'm saying neural network is permutation invariance. This property is not only at the optima point. This is for any weights, right? For any weight this holds. So I'm not saying at the optima it will be permutation invariance. I'm saying for any weights it is permutation invariance, and that's a property of neural network. The way we make it, right? And it holds. I mean, this W1, W2 need not be optima. This might be some random weight I set, but I can also change them and get the same thing. That's the point. Okay. Any question? Obviously, the nonlinearity part was also right. So you can prove that in this case it will not be imaginary, but that's a mathematical route. That's the more elegant route. I mean, that's the. But this is like you don't. I mean, sometimes you don't need the maths. You can see the things before even you start doing the maths. So this is that route.
Sir, what are we saying here that if for the first one we find the optimal W1 to W4?
No.
Then we exchange it.
No. I'm not even going to optima. I'm saying for this, even by permuting the weights, my output will remain same. So there are multiple sets of weights if I permute them, and this is only two, so only two combination you are getting. For more number of nodes, you will get more than two permutation combinations. So, so it is not that W1, W2, W3, W4 in that sequence will only give Y. There are other combinations of W1, W2, W3, W4 that also gives the same Y. Which means even at the optima, you will get some W1 star, W2 star, W3 star, W4 star. That also can be permuted to get the same Y. So that means there are two sets of, at least in this example, weights which are giving the same optima. So it's not a unique optima.
But in convex case also it holds.
What?
But in convex, the convex normal convex case, it also holds.
No. How it holds?
It's a parabolic function, multiple set of values leads to the same output.
At all values.
No, two set of values are.
How? What value are you talking about? Why are you looking at the y? I am talking about x. Is there a value of x where you are getting two values in this? This is a convex function. What do you mean it holds? You are looking at y, right? I am talking about x. Is there, you understand what I am saying? And also, does it hold at all points? It might hold at some points and that's fine. But will it hold at all points? In this case, I am not even taking optima or something, right? This is holding at any y. Will that hold there? No. At any y, it will not hold. At least there will be one point where it will not hold, even if you look at from y side, right? Which is the optima. In this case, that will not happen. This is true for any value, right? Make sense? Okay. So fundamentally, we are dealing with a non-convex optimization problem. Now, in a non-convex optimization problem, you will have local minima. I mean, if you are very lucky, maybe you have multiple global minima, but that will almost never happen probabilistically. So what you will deal with is multiple local minima and one global minima. That is what you will deal with, right? And now what is the algorithms that we are using, right? This is an iterative algorithm. So if it is an iterative algorithm, what will happen? No matter, not no matter, what will happen is that your final result will start being a function of your initial guess. If you, whatever is the nearest optima, it will converge to that, unless and until you are taking some random very big steps. So for example, if I take this one, right, let's say I have this function, okay, and let's say my starting point is this one, then there is a high chance this is where I will converge, right? If my starting point is here, there is a high chance this is where I will converge, given that I am doing gradient descent and not gradient ascent. If I do ascent, the nearest maximum is where I will converge, and same, so on and so forth. So your initialization is very important, correct? So now naturally the question is, how do you initialize your training algorithm? How do you select your theta naught? Because for this thing to hold, where is it? Yeah, this update, right? For this thing, this arrow, it need to start with some initial guess of theta. So the question is, what is that initial guess of theta? What is that good guess for theta? First of all, okay, there is no perfect guess of theta. You can only hope that you will do 3-4 runs, you will get 3-4 optima, and then maybe the best one among those, maybe average of that, is what we will have to deal with. Because you have to keep in mind that what is the number of parameters we are dealing with in deep learning. At least 100,000 or something like that. So if you are dealing with 100,000 parameters, we cannot hope to see this and draw lines and all of those things. We can, even gradient calculation is going to be very, very expensive, and we have no clue how many local or global optima we are dealing with. So we have no idea whatsoever in a 100,000 dimensional space, right? So we will not be able to do anything about that. So what we can do is hope. We can hope that we will do a few restart. You cannot even do 100 restart. Each training will take days. So few restart is probably the maximum we will do. 4, 5 is what people do. And then based on those 5 restarts, we will probably take the best one, the average one, or something like that. That is what you will have to do, right? So first of all, we should be very clear that we are not even trying to get the global optima. I mean, if you can find an optimization algorithm that can give you the global optima with guarantee, you will probably get some Fields medal. I mean, it's that big a problem. Okay, it's one of the most challenging problem to develop algorithm for getting global optima. Okay, so that with definitive proof, by the way. People claim that GA and all of those things gives global optima, but that is in the limit that you will do thousands of particles, thousands of iterations, which you will, not thousands, I mean infinite, which means you will never do that. So you will never have, you will even in that case, you don't know what optima you are getting, right? So the point I am trying to make here is that first thing first, we will have to live with local optima. Okay, we will try do some sanity check, try to improve our model and all of those things we will do, but we will ultimately, even after all of that, we will probably work with the best local optima we can get, which we will say is our global optima. I mean, we will not even say that, but anyways, right? That is the first part. But even with that, the question still remains, how do you initialize the training process? What is a good initial guess for your weights? That question still holds, and let us try to answer that question. So there are two parts. A good initialization will not guarantee you a global optima. So first, that should be clear even before we start talking about a good initializer. We will have local optima, but even then a good initializer is important. Okay, so these are two different questions, and we will try to understand, even though we are not guaranteed to reach a global optima, why a good initialization is important. Clear the question we are trying to answer? Because do not think for a moment that we are trying to get a global optima. We are not, we cannot. Okay. So in deep learning, we have no way to ensure we get the global optima, okay, or minima, whatever, which means that is why we have to work with local optima. Correct? So in DL, we have no way to ensure we get the global optima. We have to work with local optima. Some strategies are like multiple restart. Some strategies include multiple restart, but that does not guarantee global optima again. Multiple restart means you will run the same algorithm starting from different initial guess of theta. That is what it means. Okay. But even then, initialization is important. Initialization is extremely important in deep learning. Okay, this is a statement that you should be very clear about. Okay, and naturally now the question is, how do we initialize? Okay, let us try to examine what can potentially be a good way to initialize, and can we develop, I mean we are not developing, can we come up with some good initialization strategy condition on certain aspects. Okay, what is this condition on, I'll not talk about now. Okay. So therefore, let us talk about initialization. Okay. So first option, let's see. Often many people do that, not in deep learning, but in usual optimization, that you initialize with zeros. I mean, those who have done any optimization course, not a deep learning course or machine learning course, you must have done that. Initial guess, I don't know, let me take it to be 0, because it varies from minus infinite to plus infinite. 0 is somewhere in the middle, it can go either way, seems unbiased. So let us start with 0. Okay. So is that a good idea? That is the first question, right? So option 1, initialize all weights, and by the way, for this discussion we will mostly focus on weights. I am not going to take bias, same thing will hold mostly for bias. Okay, so with subtle changes. Initialize all weights to 0. Do you think it's a good idea, bad idea? Good idea. Why? Okay. Okay. So one suggestion is that the same logic should hold, right? Weights can go from minus infinite to plus infinite. 0 is unbiased, in some sense go either way. Seems like a middle point. That's a good.
It does not take loss landscape.
It does not take loss landscape into account. Loss landscape, anyways, we will not be able to find out. That's a different story. But okay, so why?
It can be biased.
It can be biased in that sense. Okay, so the other opinion is that, but I mean, it should not be unbiased in the global sense. It should be biased towards the loss landscape. I mean, it should be conditioned on the loss landscape, which we most probably will not be able to make sense out of, because loss landscape means you plot in the weight dimension. So 1000 dimensional plot, 100,000 dimensional plot, let's say. Okay. Any other thing? Yeah, I'll come back.
The updates would be similar for all the weights.
Updates will be similar. Can you elaborate?
So if we start from 0 for, say, there are two neurons, W and W. We start from 0, and the loss function, the derivative would be del by del W1. If we take the linear activation, then the derivative would be x. So after the first iteration, it will update, W1 will update as 0 minus eta times x. And the same thing will happen for W2 as well. So ultimately both the weights are they're trying to, they're doing the same thing.
Same direction, right? Okay, so let me repeat. So here the opinion is that starting with 0 is not a good idea, because if you start with 0, so every weight is basically 0 now initially. So you will get some output, let's say, but because everything is 0, the output, the derivative of that will be same, because dl by dh1, dl by dh2, whatever you do, you will evaluate at the same value, because same x, let's say, right? So as a result, what will happen? The direction will be universally same. So it will always be, all weights it will always be working with a scenario where all weights are same. But this can be extended. This is not true for 0 only. This is true for as long as the weights are same. So it is not that all weights should not be started at 0. It is that, I mean, if I extend that, this logic tells us that we should not initialize all weights at the same value. Because as long they are same, H1 and H2 is same, because they are connected in a fully connected sense. If H1 and H2 are same, Y same, so derivative same, so all W's will be same. You follow what I am saying? So that means it should not only be 0, the second point also was covered, that it should not be same, the weight should not be same, I mean, they should not be initialized at some constant value. Okay. Any other reason you think that starting at 0 is not a good idea? That is a very valid reason, and that not only holds for 0 but also for all weights being initialized at a constant value. That should also not be done.
We anyway have to initialize at different points.
Yes. Correct. So that is true, but I am asking any other reason you can think of. That is anyways true, you are right. I mean, if the second one holds, this automatically holds. But I am saying, is there any other reason you can think of? Maybe for some specific cases, let's say. So let me give you a clue, right? Let us think about activation function, because ultimately initialization is also function of activation function. What will happen if my activation function is sigmoid? You initialize at 0. So w times b I am not considering, w times x is 0. Sigmoid of 0 is 0.5, 0.5, right? Sorry, not sigmoid, let us take tan h actually. So in tan h, sorry, sigmoid, yeah, it is fine actually. Sigmoid of 0 is not 0.5, it is some negative number actually, right? Or 0.5, e to a 0, I think 0.5, yeah. E to a 0 is 1.5, right? So if you start with that, let us say you are in the tan h, right? In tan h, that will become 0. So you are out in tan h, it will again become 0. So for tan h, for example, it is not a good thing. Let us think about ReLU. In ReLU, what will happen? It is not only 0, at that point the gradient can also be flat, dead unit. You remember ReLU, the dead unit problem, straight and then, so this not only it is 0, it is also, it won't update in ReLU. So you have to be careful. You should not initialize at some point where it will stop updating. And let me elaborate on that further, right, with examples. So, not a good idea. In fact, to initialize all weights at same value, including at 0. So it is not a good idea, as correctly pointed out, to initialize all weights at same value, including initializing all weights at 0. Also, for specific weights, specific activation function, activations, zero initialization might lead to dead unit. Okay, which is a ReLU case, for example, right? I am only letting a ReLU case, but there can be others case also. Okay, going ahead. So what will happen if I initialize the weights to be very large value, either on the negative side or on the positive side? Now this will be very case specific, but try to think. So they are not same, but I am taking very large value in most of the cases. Why? Yeah, go ahead. Exactly. So I said sigmoid, let's take. Very large value, the gradient has saturated. So there is no gradient there, no update. Very large negative value, same story. Same story holds for tan hyperbolic also. So again, depending on activation, at least the popular two activation we can see, initializing at very large value is probably not a good idea. Okay. So the second thing is initializing at large values, either positive or negative, I am not writing that, will make gradients 0 for we said sigmoid tan hyperbolic like activations. Okay, just to remind you, sigmoid looks something like this. Okay, tan hyperbolic looks exactly the same, but and you can see what is happening on the extreme right and extreme left. It's almost flat, asymptotic. So the gradient is 0, saturated gradient, saturated unit. No gradient means no update. Wherever you start, you stay there. Make sense? Any question? Okay. Thirdly, what can you think of a case where initializing negative value is the issue? ReLU, we just discussed already. Initializing at negative value is not a good idea if it is a ReLU. I mean, it will always be 0, gradient will always be 0. So the third one is initializing at negative weights. I will not be able to complete the initialization today. Weights is not a good idea for ReLU. Okay, and I can have other observations also for different activations. But let us not go there, but try to summarize what we discussed. So, can you tell us what we summarized here? Or can you summarize? We did not summarize anything, but can you summarize from this discussion some points? First one is avoid extreme. Why should I avoid extreme for, let's say, ReLU, positive extreme? Just a quick. So, I want to generalize, right? So, first comment was already generalized. You should not initialize weights to be a constant value. No matter that is 0, non-zero, does not matter, it should not be constant. That is a global observation for any activation. And the second activation is, second observation is that initialization is activation specific. If activation changes, initialization needs to be adjusted accordingly. Because the observations are not global. Like the extreme, the extremes we should avoid, correct. But for tan hyperbolic and sigmoid, negative we should avoid, correct. But for ReLU. So these observations are turning out to be activation function specific. So two observations, it is activation function specific and it should not be initialized at the same value, right. So broadly, two observations. So the first observation is should not be initialized at a constant value. The second thing is initialization is activation function specific. Okay. So broadly, two comments, two observations. Should not be initialized at a constant value. Initialization is activation function. Specific or it is, dependent or conditioned on that. Yeah.
But should be something like all the weights and all the things should be not constant, same constant. Because
yeah, that's what I meant.
possible
That's what I meant.
different
Should not be constant means all the weights. That's what I meant. Ultimately each weight is a constant value, right?
Yeah.
So when I say should not be constant, I mean you should not be set all weights in a layer at a constant value, even at a layer. And obviously layer to layer is still okay, but at in a layer definitely they should not be constant, right? These two observations are clear? Okay. So then the question is, can we derive, for example, a good initialization strategy for, let's say, tan hyperbolic case? And I am taking tan hyperbolic because it has been derived by someone, obviously that is why I am taking it. Similarly, there is same derivations which I will not do, but you can look into it, is for ReLU also it exists. Okay. So, can we come up with some good initialization strategy for let us say tan hyperbolic, right, because it is activation function specific. But even if we do not come with, will you agree that a good solution or a good initialization is that I initialize it randomly, because then it will not be same? Will you agree that the mean of that randomly initialization can be 0 in most cases? Most cases ReLU might create problem, but that is why I am saying most cases, right? I mean, again, it can still be random, but it should not be 0 mean, okay? And then the variance would be adjusted based on the activation function. So, based on this, will you agree on these things? Let me repeat that it is a good idea, or it is a practical idea at least, that we initialize the weights randomly, right? First point. Second point, it is also practical in most scenarios, at least for tan hyperbolic, let us say. It is a good scenario or a good practice to initialize it at the mean of the random variable at 0, because tan hyperbolic is I mean odd function. So, positive and negative, the sign changes. So, it exists on both sides. So, 0 seems like a good thing, even for, I will say, sigmoid also. I mean, 0 seems like a good mean value. Same thing, because it varies from -1 to 1, or in that sense, right? Okay. Third, now the variance, and variance needs to be adjusted, and variance have to come from the activation function we are using. So, these three observations make sense to everyone. So, let me write it down. If you have any doubt, feel free to ask, right? So, based on this, the observations I am drawing is that practical solution is to initialize weights randomly, right? Now, what is this random distribution? I am not specifying. It can be uniform, it can be Gaussian. I mean both are possible. Let us say most of the time people do Gaussian because I feel that Gaussian we are most familiar with, but you can also do it uniformly, and it is done uniformly as well in some cases, but randomly, because that ensures that they are not same. You take 10 samples, they are different. So, randomly. Then I said for tan H and sigmoid, the random distribution should be centered around 0. Make sense? At least for tan hyperbolic I am saying. Okay. Make sense? Now, what does 0 do? It does two things, by the way. One is that because it at the middle of the things, the gradient is, I mean, very sharp. So, you do get a good gradient, and also remember that at that portion it is almost behaving linearly. I mean, near the 0 portion, tan and sigmoid both are behaving almost linearly if you look into the curve. I mean, the curve I drew, right? Yeah, both these curves. Look that around 0, little up, little down, it is kind of behaving linearly, right? So, the gradient is a straight line or constant gradient that you are getting, which is a good thing actually for object. two observations, these were two observations, there is one more, right. So, this was 1, this was 2, and the last one is the variance needs to be determined, the variance needs to be determined based on activation function we are using. Okay. These observations, any question? So, if no question, let us start with the derivation of tan optimal initializer in some sense for tan hyperbolic. Again, given that only 20 minutes are remaining, I will not be able to finish it, I am pretty sure of that, but it is okay, we will continue it next time. Okay. So, initialization for tan hyperbolic activation. Okay. Initialization for tan hyperbolic activation. Okay. So, before we proceed with that, let us set up the problem. Okay. Because remember, we are talking about not a single layer kind of thing, we are talking about a generic large deep learning model, maybe 10 layers, 50 layers, 100 layers, something like that. So, let us set up the problem, and for setting up the problem, let us assume that we are at the lth layer and we are computing the lth layer from the L minus 1th layer, I mean as you do in a neural network, right. So, I am just setting up the problem. Okay. Consider we or rather let us say consider the ith neuron in the lth layer. So, we are just focusing on a single neuron which is the ith neuron, but in the lth layer. First layer is the, by the way, 0th layer is your input layer, first layer is your first hidden layer. So, like that 0, 1, 2, I am at the lth layer and I am concentrating on the ith neuron in that layer. Everyone follows what I mean? Ith neuron in the lth layer. So, think of a neural network, one of the neuron in one of the layer. Okay. So, how do you what is the computation that is happening here? So, there is the computation of Z, which is the pre-activation, and then you apply the activation function on that, right. And activation function for our case is tan H. So, because we are there Z lth layer ith neuron, how will you calculate it? Z is basically the linear portion, pre-activation. How will you calculate it? You know it already, summation Wixi, right. So, the same things would happen, but can you tell me the expression as a summation, not vector notation, just summation. It will be summed over what? Each of the neuron in the previous layer, sum over each of the neuron in the previous layer. So, let us say that is J, and then there will be weights connecting, I am writing L here because I am going to L, connecting jth neuron to the in ith one. So, jth neuron in the L minus 1 layer to the ith neuron in the lth layer, multiplied by H L minus 1 I no J Okay, let me draw it so that it is clear, but it's not that difficult actually. So let's say this is like this, right? Okay, so my network is like that, and I'm only focusing on this neuron. Okay. So what is happening? I want to compute the z of this one. So I should sum over what? Each of the 3 lines I am seeing. So that summation j should go from 1 to 3. So what is 3? The number of neurons in the previous layer. So that is what we am doing. And then what is the operation? W connecting the first one to j, second one to j, third one to j. So this weight, and this weight. So this weight multiplied by this one, this weight multiplied by this one, this weight multiplied by this one. Okay. So this is what I have written in summation form. Check carefully if this is clear or not. If this is not clear, I can even write that one. Is it clear? Okay. Great. So this is the operation that is happening. And then one more operation is happening, right? What is the other operation? Activation. The simplest one. Not every operation will be difficult. H L I is equal to tan hyperbolic Z L I. Okay. So these are the 2 operations that are happening. Okay. Now, here is a proposal from my side. I am going to propose that this Z, H, W, all of these are random variable. All of these are random and random variable. Now, why am I calling it random variable? Let me explain. Okay. W I am calling random variable because I am initializing it randomly. We discussed that we can initialize it randomly. So if you are initializing randomly, that's a random variable. That's the easier one to understand, right? Why is H a random variable? H is a random variable because H depends on X. And in my X, I don't have one data point, I have multiple data points. So you can imagine that data I have is like a samples of a random variable. So if I start thinking of it that the data samples I have are samples drawn from a random variable, then my X is a random variable. If my X is a random variable, H becomes a random variable, all the H. So W and H both are random variable. If W and H both are random variable, Z will be a, if Z is a random variable, H will be a, again, H was a random variable in L minus 1, H at L will again be a random variable. So I am going to propose, or I am going to suggest that you imagine all of these things as random variable. Okay. Now what will happen if the variance of this random variable becomes very small? Look at it and try to answer. I have trained the model, but after training the model, or even before training the model, my variance is very low.
Lose that gradient because the things will come.
Even I think even severe problem is there, but that is a correct thing. But even severe problem, think about it. If the variance is very low, what will happen? Variance, a random variable with 0 variance, what does it mean? Deterministic, constant. So a very low means the variance is very low, almost same value it will start giving. No matter what X you are giving, output is same. Right? No matter what X you are giving, output is same, and that comes to your problem. Now the sensitivity is 0, so you are at a problem. Right? So a very low variance is the issue. Now what will happen if the variance is very large? Huge variation, huge gradient, even bigger gradient. So that is known as the blow up problem. I mean, it will go anywhere because the gradient is so large, it will just blow up, you will not be able to train it. So what do you want? optimum variance. What is optimum variance? Think about it, this L, I mean the number of layers, let's say that was what, M I was using, I forgot what I was using. K was the number of feature, N was the number of data point, I think M. So number of layers M, right, is 100. So what will happen? Even if the variance is for each layer is 1.1, and if they keep multiplying, it will be that, I mean you saw that, I think meme or post, right, 1.01 times 3 to the 65 is a very big number. So that 0.01 matters. So same thing will happen here. 1.01 times, let's say 365, or in this case 100, is a very big number. So it will blow up. And 0.99 times 365 is a very small number, or times 100 in this case is a very small number. So what do you want? You should want that the variance of each of these layers would be as, I mean, it should be 1 ideally. The variance of each of these layers would be 1, so that even if there are infinite number of layers, theoretically, again, it will still be 1. I mean, the output with respect to input will still remain to be 1, right? Obviously, here I am assuming a lot of things, I will have to derive this, but obviously I will not be able to derive today, so I am talking about the philosophy today. This derivation I will show next time. I am not even trying to start the derivation, but I am trying to show you or tell you that how we can approach this problem. So this problem we are going to approach as follows. Tan hyperbolic, so I will take the mean of my random variable to be equal to 0. Make sense? Let us take it to be Gaussian, because both side, right? So Gaussian with 0 mean and variance sigma w, right? And now I know that the output variance would not blow up or shrink no matter how many layers I have. So we have to work with that, and by working with that we should be able to find out, hopefully, some reasonable way of setting the value of sigma w. So let me write down the problem statement again. I am not solving today, I don't have time. So yeah, so what I am saying is as follows. See, so the first thing I am saying is, because it's tan h, we initialize each weight and each weight independently. We initialize each weight independently with Gaussian 0, sigma w square, where sigma w square is the variance of the distribution from which I am sampling my weight initially. Okay, clear? And then I am saying the next thing, we don't want our model or model gradients, let us call it here, to either blow up. We don't want our model or gradients to either blow up or shrink. When I say blow up, I mean approach infinite. When I say shrink, I mean an approach 0. We don't want that, right? So now the question is, by combining these two factors, so the objective is to find out sigma w that ensures this thing. So therefore, the goal is, and I will stop with this one. So therefore, the goal is find sigma w that ensures the condition above. Okay. This is the goal. I will stop here. We will start with this thing only. We'll start with this thing, right? Ith layer and all of those things. So this portion will repeat, and then we'll proceed with finding out the a good sigma w for this thing, right? Okay. Thank you.